Guys, this is the Nuclear Physics Review. You know already that there are three subatomic particles, the proton, the neutron, and the electron. These circles are to indicate how big they are relative to each other. The proton and neutron are very close to the same size. The electron is much smaller. It says size exaggerated, so relative to these two, that's even too big. The mass of a proton and neutron are very close together. Actually, if you carried the neutron mass out a little farther, it's a little bit more massive than a proton. The electron is 9.1 times 10 to the minus 31st. So look at these exponents, minus 31st and minus 27th. So that's like 6 powers of 10, or could be 4 powers of 10 difference. So protons and neutrons are many times more massive than electrons. Neutrons, you know, have no charge. Electrons and protons have the same charge, 1/6 times 10 to the minus 19th, positive on a proton, negative on the electron. So the symbolism that we use to represent elements looks like this. The X is the chemical symbol, and so Na for sodium, like in this case. So the symbol of the element goes where the X is. A is the mass number, and that is the number of nucleons. Remember, protons and neutrons make nucleons, things in the nucleus. Z is the atomic number, and it is the number of protons, and that's what identifies the element. On a periodic table, you'd see a rectangle that looked like this. The 11 is the atomic number, so again, the number of protons. Na would be the chemical element symbol, and then typically the element name is written. And then 22.99 is the average atomic mass. So this with A tells you the isotope that you have, or how many neutrons and protons together. So A is number of neutrons, nucleons, Z is number of protons. So A minus Z would be equal to the number of neutrons. So A is protons plus neutrons all together. And so this talks about a very specific isotope of the element, where on a periodic table, this is the average atomic mass of all of the different isotopes of that element. So what's an isotope? These are three common isotopes of carbon. This would be carbon, actually we would call it carbon 12, but carbon, basic carbon, the most common carbon 13 and carbon 14. Notice same number of protons in each because it's the proton that actually determines what the element is, but different numbers of neutrons. So you can have an atomic number of 6 and a mass number of 12, or a mass number of 13 or a mass number of 14, depending on how many neutrons you have. The natural abundance of an isotope is the percentage of that percentage of all of the atoms of that element that are that particular isotope. So out of all the carbon that there is, 98.93% of it is carbon 12, 1.07% of it is carbon 13, and about 0.01% is carbon 14. And this is called the natural abundance of those isotopes. What is a mass unit? The mass of a proton is 1.007276 U, or mass units. They used to be called AMU, or atomic mass units, but now they're just U. And what they did was they took a carbon 12 atom, and they said that 1 U is equal to 1/12 the mass of a carbon 12 atom. And so the mass of carbon of a carbon 12 atom is 12 U. And the mass of a carbon 13 atom would be 13 U. So it's another element of, another unit of mass, and it's based on the mass of carbon 12. Protons and neutrons both have a mass of about 1 U, and an electron has a mass of 0.00055 U. Binding energy. So remember the formula E equals mc squared. We'll talk about it a couple of times today. The total mass of all the atomic particles of an atom is always more than the actual mass of the atom. the mass deficit, the difference between the sum of the particles and the atom mass, it's called the mass deficit, and it is mass that has been converted to energy that is holding the atom together. Remember, in the nucleus, you've got protons close together. Protons are positive and they're repelling each other. And so this binding energy has to hold those positive things together in a very small area, even though they're trying to repel. So this example is a helium nucleus, which is also called an alpha particle, which we'll talk about more later. An alpha particle is a doubly ionized helium atom or a helium nucleus. It has 2 protons and it has 2 neutrons. So to get its mass, you would do 2 times the mass of a proton plus 2 times the mass of a neutron. This is the mass of all the parts of an alpha particle, but an alpha particle only has this much mass. The difference in those is the binding energy in U. It's often expressed in another unit called the electron volt. The electron volt is the amount of energy gained when one electron is moved through a potential difference of 1 volt, so 1 electron volt. 1 mass unit of mass has 931 mega electron volts. That would be 931 times 10 to the 6th electron volts of energy. And 1 electron volt is 1.6 times 10 to the minus 19th joules. If the total particle mass, okay, this is back to the alpha particle, if the total particle mass is 4.03188 U, and the alpha particle mass is 4.00153 U, then the mass deficit, or the difference in these, is 0.03035 U. And if we want to convert that mass into the equivalent energy in joules, because of this formula, E equals mc squared, we can kind of talk about mass and energy as being interchangeable. And so to talk about the energy of this much mass, it's just using this equation or this conversion. So we take the mass deficit, that's this, and it is in U, and we convert that to EV by multiplying it by 931 times 10 to the 6th EV per U. Notice then the U's cancel out and we have EVs. And then we convert that to joules by using the 1.6 times 10 to the minus 19th joules per EV. And we have 4.42 times 10 to the minus 12 joules. This is very similar to an example that's done in the course content. There are 3 common types of radioactive emission. There's alpha decay, beta decay, and gamma decay. In alpha decay, a unstable nucleus, that would be a nucleus that doesn't have enough binding energy to hold it together, gives off an alpha particle and becomes a stable or a more stable, a smaller nucleus. What you start with is called the parent nucleus, and what you end up with is called the daughter nucleus. And so if it gives off an alpha particle, the particle looks like this. Remember, an alpha particle is a helium nucleus. So it's got 4 nucleons, it's got 2 protons. And so if you start with something that looks like this, and you're going to give off an alpha particle, you can't just, particles don't just disappear, and so you have to have conservation going on. So if the alpha particle is going to take 4 nucleons, then the atomic symbol will be the original mass number minus 4, and the original atomic number minus 2. It's going to take 4 nucleons altogether, and 2 of them are protons. So that's how that decay equation is written. Beta decay gives off a beta particle, which is just an electron. But what really happens is you have a neutron converting into a proton and an electron. And so you have the same number of particles in the nucleus, the same mass number, because a neutron converted into a proton, and so the A doesn't change, but you have an additional proton. So the element is the next element up in the periodic table, and you get a beta particle off. Conservation of charge happens as well. A neutron has no charge, a proton has a charge of +1, and an electron has a charge of -1, so we have conserved charge as well as conserving mass and nucleons. And then gamma emission, it doesn't really give off a particle at all, it gives off energy. So you have an unstable nucleus, and that we say it relaxes down to a stable state by giving off some energy in the form of a photon. Very high energy photon. It's very dangerous radiation. Okay, and actually I just kind of said this. Alpha decay, remember it gives off a helium nucleus. So you're going to take 4 away from the mass number, and you would get 222 minus 4 is 218. And then you would take 2 away from the atomic number, and 86 minus 2 is, excuse me, 88 minus 2 is 86. And then you'd look on your periodic table to figure out what the element is. Alpha particles are big. They could be blocked by a piece of paper. Beta decay, this is an example. Remember, a neutron converts to a proton. So your mass number stays the same, but you get 1 more proton. And charge is conserved because even though I have an extra positive thing here, I have a negative thing here. Beta particles are pretty small, but they can be blocked by 3 millimeter thick aluminum plates. Gamma emission, this just says this is a nucleus in an excited state, and it relaxes, so your nucleus is the same. Now, sometimes they're more complicated gamma ray. If you look online, you might see more complicated equations where it actually does break into a daughter nucleus. But in the simplest case, the atomic nucleus stays the same, and then you just have gamma ray. Gamma rays, 8 centimeters of lead can block a gamma ray. So from least dangerous to most dangerous. Half-life is the amount of time required for half of a sample to decay. The change in the number, N is the number of particles. The change in the number of particles is equal to lambda, which is called the decay constant, times the number of particles that you start with, times time. If I divide both sides by time, the change in particles divided by the change in time, that's a rate, and it's called the decay rate, and it's equal to lambda n. So the decay constant times the number of particles that you start with. And if you want to find half-life, the half-life, or time for half of the sample to be gone, is equal to the natural log of 2. This is not log base 10, but ln2 divided by the decay constant. And the natural log of 2 is 0.693. So the equation is half-life is equal to 0.693 divided by the decay constant. Or you could get the decay constant by dividing 0.693 by the half-life. Okay, so an example, if carbon-14 has a half-life of 5,730 years, what's the decay constant? What's the decay rate? You started with 10 to the 22nd atoms. So first thing, we need that half-life in seconds. So we're going to say 5,730 years, the conversion here. And in 1 year, there are 365 days. And in 1 day, there are 24 hours. And in 1 hour, there are 3,600 seconds. And so 5 times 24 times 600, that's a lot. That is 1.81 times 10 to the 11th seconds. Okay, so let's go back and look at the equations that we had. So we have the half-life and in seconds, and so it's 0.693 divided by the decay constant. So the decay constant would be 0.693 divided by the half-life. So 0.693 divided by 1.81 times 10 to the 11th. It's going to be really small. Divided by 1.81. 3.8 times 10 to the minus 12. Okay? And what is the decay rate? Well, in the last slide, we said that the decay rate was lambda times the number of particles that we have. And delta n over delta t equals lambda n equals 0.83 times 10 to the minus 12 times the number of particles, 10 to the 22nd. Let me do this in the calculator. I get 3.8 3 times 10 to the 10th minus 10th. And the decay rate units are becquerels, or BUs. After one half-life, half the parent nuclei have decayed to daughter nuclei. After 2 half-lives, what fraction is left? Well, at the end of 1, you have half, and then half of that, well, you have a fourth. And then half of that, after 3 half-lives, you would have an 8, and so on and so on. This I just picked up from the course content because it was as good as anything. Looking at a graph of the decay substance, you can determine the half-life by the time it takes to decay half of any amount. So if you have the graph, and this is time in hours, then it takes 1 hour, in this case, 1 hour for half of the substance to be gone, so the half-life is 1 hour. This only works for large samples. Decay rates are based on probability and may not work if your sample size is small. Fission and fusion. Nuclear reactions can happen when small things come together to make big things. Deuterium and tritium are both forms of hydrogen, 1 proton each. Helium is bigger, and if these 2 small atoms smash together fast enough under enough pressure, they can create this larger this larger atom, give off a neutron, and make some energy. Fission is when a large nucleus breaks into smaller nuclei, and it takes a neutron to make that happen. You toss a neutron in, and it causes that fission reaction. It breaks into 2 smaller parts, plus you get 3 neutrons in the deal. Remember that E equals mc squared thing. Tiny bit of mass converted to energy can be a lot of energy. You can use this formula to find the mass needed to achieve a certain amount of energy. So if you are given energy and asked to find mass, you can do that. This is just our kilogram, and this is joules, and this is meters per second. So numbers that you're used to working with. So going back and forth using this equation is very, very easy. Okay, fission happens when, as I said, one large nucleus, when bombarded with a neutron, breaks into 2 daughter nuclei and 3 neutrons. This is the decay equation for the fission of uranium-235. Notice there are 3 neutrons produced. So if you have a whole bunch of uranium-235 and one of them undergoes fission, it supplies 3 neutrons that can be used to make 3 other uranium-235 atoms go through fission themselves, which will then produce 3 each. So that'd be 9 more neutrons to make more uranium go through fission. And so it's a chain reaction. And if it's uncontrolled, think nuclear bomb, that could be bad. The minimum mass of material needed to start the chain reaction is called the critical mass. Now, we use fission in nuclear power plants, and it would be bad if we couldn't somehow control the production of neutrons, but we can. We use control rods. These are materials that absorb neutrons, and because they can moderate, we can keep enough neutrons to keep the reaction going, but we can keep the number of neutrons down so that we don't lose control of the reaction and get a meltdown. Fusion happens when 2 small things fuse together to make one big thing. It's fusion. Fusion is the process happening in the tremendous gravitational pressure and high temperatures of stars. Because both of the hydrogen nuclei are positive, they must be under very high pressure or moving very high speeds, so the pressure and temperature of stars are sufficient to make this happen. We don't make fusion happen on Earth, except at very high cost. It takes a lot of energy to cause a fusion reaction to happen. So fusion is not, it's an ideal energy source because this is stable. It's not a radioactive end result of this reaction. The product is stable, and so it'd be great, but it takes lots of energy to make these 2 things squish together to make this thing. So until we find a way to have cold fusion, fusion at temperatures that are not really, really high, and make this happen at some reasonable cost, this is not really a reasonable energy source. And that is the end of our nuclear physics review.